Right guys, I just thought I'd do a question 0 here, which is just like a bit of bookwork, so I better put the bump for bookwork that's needed. Okay, for these 20 questions, we're going to do turning points. We're going to do 20 cues on turning points, and then we might as well do some sketching as well. So we'll use what we need to sketch the curves, alright? So turning points then, that means when the curve turns. So for example, suppose we have a curve. So I'm going to draw a picture of a graph now. Suppose we've got this. I'm just going to look at this, for example. Suppose our curve looks like that. Here's our x-axis. Here's our y, which we'll call the outputs. The x we'll call the inputs. And here's our axis, like so, yeah? So suppose we've got this curve here that's generated when we plot a function. All right? Okay, well, at any point you've got to measure the slope of the curve. Like you can imagine yourself, if you physically think of this as being forwards positive direction, you can think of yourself as a person moving along in the positive direction, can't you? And you'd be traversing a hill. Now, if you're doing that in the real world context and you saw this signpost, 1 in 3, that would tell you how steep the hill was, wouldn't it? If you were driving your car, you'd know what gear to get into. It's quite a steep hill, isn't it, 1 in 3? What does that mean? Well, that means for every 3 units you go along, you go up 1. It's not the size here that matters, it's the proportions. So for every 3 units, however big those units may be, you go up a corresponding 1 unit vertically, don't you? And that gives you your measure of your slope then, yeah? 1 in 3 hill. The tangent of this angle is 1/3. That is a measure of the gradient. So if you had, say, a 1 in 2 hill then, which is even steeper, isn't it? I don't know if you meet many roads that sort of slope. Let's draw it. For every 2 you go along, you go up 1. So I think it's going to be a bit like that, isn't it? Can you see? That's going to be steeper, isn't it, than the preceding slope. That's a 1 in 3 hill. This is a 1 in 2 hill. So the tangent, again, the slope would be 1/2. Steeper. It's a bigger value than the 1/3. So you can see what happens here, can't you? If you're on this hill and you're driving up here, for example, it's really, really steep. And then it gets slightly less steep. And then at the top here on the brow of the hill, it flattens out. So the question is, that's called a turning point in a curve. Just as you would turn over the top of the hill when you're driving or walking over a hill or driving a car over the top of a brow of a hill. And this actual thing here is called a local max. Some local maximum, alright? By the same token, a little valley, like so, would be a local minimum. Now the point is that dy dx is a measure of the gradient at any particular value. And we've been working out lots of dy dx's, haven't we? Is a measure of the gradient. Gradient at x. Alright? So here, if you put the x value in here, you'd get a steep. If you put that x value in, you can see that the tangent is steep, can't you? But if you put this and then it diminishes, and then you put this x value in here, you'll get the y dx is flat. Now what slope is that? What measure is that? Well, let's just draw a picture of it, shall we? Pictorially speaking, we can draw it like this. So if that were 1 unit, if that's flat, how much up have you gone? Well, I know I've drawn it illustratively here. You've gone up 0, haven't you, because it's flat. So by the same token, whether you worked out the 1 in 3 was 1/3 for a 1 in 3 hill, this hill is a 1 in 0. And it's that way around, isn't it? It doesn't matter which way around you write these numbers, because a 1 in 3 is different from a 3 in 1 hill. Totally different. So 1 in 3 hill, so this is 0 in 1 hill. So there's the gradient or the tangent, and that 0/1 is 0, isn't it? So you can see at the top of the hill then, the point is that if you find out when dy dx is 0, you've found out the value of x when you've got a flat spot. So here's another one. Here's another flat spot. So dy dx is 0 at local maximums and local minimums. Now I'm going to talk about the second derivative, but I'm not going to do that here because I don't want to drag it out. I'll spend too long talking about this stuff. But I'll come back to this in subsequent questions, probably question 2 or 3 or something. But here, to get a local maximum occurs when the second derivative d2y by dx squared. If that's negative and dy dx is 0, you've got a local maximum. And here, if d2y by dx squared is positive, and that is 0, then you've got a local minimum, alright? So that's the key. Those are the things we're looking for very closely. And as I say, I'll say more about the details in due course, but that's enough for now to be working with, alright? And we'll come back to what the second derivative means. This is just the way of writing the second derivative. I just mentioned it here. We write d2y by dx squared. All that is the second derivative. It's d by dx of dy dx. That's what it is. And we generally write all that long-winded thing in this more abbreviated form. It means the second derivative. You're differentiating dy dx to get the second derivative. That's how we describe it. Okay then, so let's get stuck into question 1. We'll do 20 of these, and hopefully by the end of 20 questions, we'll know all the little nuances, probably most of the nuances, subtleties, and the problems we can come across. And we'll do a few little bits of curve sketching. We'll use what we need when we do these things. Okay then, so let's go on to our first question then. Great.